A couple more people wanted to join. Okay. Do you want to participate in the meeting, Ed, or just streaming? Okay. No, that's fine. I just wanted to make sure. Okay. Well, I think we've got a couple people we can start. So yeah, discussion was to see if we can find a good fix for the memory issue that Brian raised. So it's issue 94990 if you open it again. But the idea is some particular usage of custom autograph function lead to a reference cycle that basically leaks. And so the more you use that, the more it leaks. That's pretty bad. We have a quick fix, but it's pretty finicky to do. Did you actually manage to land it?
Yeah, landed over the weekend.
Okay, so we do have a fix, but it's pretty finicky to do. And the idea is to try and see if we can do a better fix. And in particular, Python as a garbage collector, and the whole point of the garbage collector is to be able to collect these kind of cycles. So the question is, can we teach the garbage collector to do it properly? Yeah, so I think we can start by, if anyone has any question about the Python garbage collector, or any question about this whole thing in general, we can get that out of the way. And then the plan is to basically dive into C++ and Python binding in general. So I want to basically show the code, show how to read it, and do a big diagram on the whiteboard of like what is a reference to what. And then from that diagram, hopefully we can figure out a way to break the cycle, or like to make the GC know about the cycle.
2 questions.
Yes.
One, is it common that the garbage collector doesn't work sufficiently, which is why Ed was like, I bet it's a ref cycle? Like, is that just a thing that has happened in life a lot?
In our life, yes. In a usual Python user life, no. The reason is most of the Python objects are set up so that they communicate to the GC properly. Mm-hmm. But our objects, we know there are fairly cases where we cannot communicate to the GC everything. In particular, the one thing you want to communicate within this traverse function is, what do I owe? What do I own? Meaning that if I died, what would I free up as I die? And we have 2 problems for that. One is that this can be expensive for us. So, usually your loss tensor through the autograph graph owns, the whole autograph graph, including all the internal buffers. And so you don't want to traverse the full graph every time you traverse these tensors, because that could be very expensive. And so there are some of these things where in the C++ world, we don't traverse everything we own directly. And we hope, or like we try and set up things so that you will never create such a cycle. So it could be too expensive to basically do the full check. And 2, we also have some problems where we have a lot of C++ objects involved. And so who owns what is a lot trickier to answer. And also because C++ doesn't have a GIL, unfortunately, well, you can have arbitrary multi-threading issues, which makes the question of who owns what even more complex. Because, in a multi-threaded world, it could be happening in different orders. So we need to be super careful when we say, I definitely own that other object to the GC.
Okay, and then the other thing is I'm looking at Brian's fix, or what it looks like. And is it just like basically breaking any potential cycles?
Yes.
Okay.
So yeah, Brian's fix is basically saying, yeah, we just break that cycle, and that's it. because we identified roughly where the cycle is at this point. But yeah, okay. Any question from other people? Okay. Okay. So, well, let's go into the code then. Shit, right. Okay. We do two things. First is camera. Good. And two. Okay. Here you go. Well, okay, actually. Yes. So the question here is, so we have a custom function. We have a custom function, we have the usual undergrad stuff, and we have view stuff involved. How do we do that? I think we can just go through these first. So, Brian, do you remember exactly at a high level what that was?
Yeah.
So it's
you might want to scroll down. The minimal repro is like near the bottom of the issue.
Yeah.
This is like the giant Dynamo version, and then there's like a 3-liner.
Yes, this is the
and the code for it is like right above.
Yeah. So on a high level, okay, let's do some nice colors. So we have a tensor object that has a grad fn that is going to be our sum up backward. Right. This one is a saved tensor. That is another tensor that has an photograph meta. Let's call that AM. That is a base. That is this one, right? Yes. Okay. Perfect. So, first thing I want to find out again is, so on the tensor side, the link between C++ and Python can be twofold. We can have both the, okay, let's say red is C++ and green is going to be Python. So we can either have the C++ object that owns the Python one, or we could have it the other way around as well. So that's this, PyObject preservation we do for tensors, so that even if so this is the regular one, this is the default. So by default, from within the Python world, we own the C++ object and we do a bunch of stuff with it. The problem is that if all the Python reference to this die, then this, in the old world, this would just go away and we only have the C++ object. But then what happens if we're asking for another Python object? And so now we have this intermediary state where when there is no reference to the Python object, this swaps around, so the C++ owns the Python. And the next time you try to get the Python object, we actually swap back here and then return the new Python object, so that we know that there is only a one-to-one correspondence between the two. So the ownership here can be both ways, which is annoying because we need to check every time. And as we'll see in the traverse code, we do very different things depending on what owns what. Then there is the case of the custom functions. And this one is a bit complex. In particular, so we have two things. We have the Python CPP functions that does some stuff. And we have the Python functions. So let's start with the Python function. So the Python function is this PyNode object.
And dumb quick question, is this literally, like in Python, does this correspond to _grad_fn? Like this is the C++ object represented by that? If I have a Python tensor and I do like t.gradfn.
Yes. So this is, so PyNode is one. So you have PyNode that, and that one I need to figure out, that is always going to be linked to a subclass of autograd function. So PyNode is only for custom autograd functions. And in this case, the ownership goes owning. So in this case, the ownership goes this way. So this is the Python object. No, no, the other way around. Okay, I never know. Yes.
So in my head, I'm picturing that as like if I have a tensor t in Python, and then I can access the t.gradfn field. The gradfn field is the PyNode in red. So that I have a pointer kind of from t to PyNode, and that's like the Python object. And then I have another pointer from the PyNode to the C++ object, which is the actual like autograd function in C++.
So there is actually two distinct cases here. There is the custom function, and there is the nodes coming from cogent code. So this is the custom function case. So in the custom function case, we do always want to keep the Python object alive. And so we own it from C++, is my current read of this. Okay. And that's where Python CPP function is different. And I think these ones will find them in function H. H, where you see a whole bunch of these things. And all these are traceable functions. No. These ones we do. So we create all these types on the fly, basically. For simplicity. Mm-hmm. Okay. So this is a janky stuff to create a Python object type. And particularly, see we have the methods with everything. We have these traverse. Okay. And so these traverse, okay, the reason why I look at the traverse here, because the traverse is a relatively easy way to know what we own and what we don't. So here, this is the C++ object, but from the Python object point of view. So the C data here corresponds to the C++. This one is going to be a regular node. I think in this case, we create one of these THP CPP function.
And this is like the cogen autograd, like backward.
Yeah.
Case, okay.
And in this case, we do have a bunch of pi hooks. So here you see that, yeah, everything that is on the function to physics. Oh, yeah, okay. Oh, this is very, okay. This is very hard to read. This should read this way, okay. So here, importantly, this is a shared pointer to C data. And that means that this goes this way.
Got it. And can you explain one more time, how is my mental model of like, just in Python, I have a tensor and I can access its gradfn.
Yeah.
Where does that fit into
Well,
these arrows?
The gradfn object will be either this one or this one.
Okay, that makes sense. T.gradfn's graphen is the green thing.
Yeah.
That points to the C++ node.
Yeah. So the green thing is always the thing you get in Python. So the thing is here, when you access this, we're saying, well, we don't really want to keep this alive. And that's why for you, we have all these metadata shenanigans on nodes. So on nodes, you have a dot metadata on this object you can use to store anything you want. That's because if you lose all the reference, this will actually get destructed and only the node remains. And if you ask for the gradfn again, you will get different objects every time. Contrary to tensors that swap the ownership and stuff. So this one, every time you access gradfn, you will get a brand new object if you didn't keep the other one alive. Because it will die if you don't reference it from the
Got it. And is the important thing here, we're saying that the THP C++ function dying does not mean the node should die, because we might be only in C++ and like all of the Python objects might be gone.
Yeah.
And that's why we have a shared pointer. So we
So here there might be other reference from, like all of these might and will usually have other references from C++ that can keep them alive. And that's where also the problem is because these could have reference from Python keeping them alive as well. That is possible in basically every world.
Right.
And when you access this function, actually you can if you try hard enough get into a weird state where you have a function but this is gone. It's very hard to do, but you can just get a reference to that, hold on to that, and then destroy the C++ graph. So usually by just del the lots, so that the whole graph gets deleted and as part of the graph getting dies. And after you do that, if you try to use that custom, it will raise a nicer telling you, hey, the graph is dead. You cannot use this Python object anymore. So we handle that nicely here.
And that can only happen in the custom function case because the direction is switched.
Yes, because if you do that here, then the whole graph will die, but this will stay alive because you have an owning reference to it. Yes. Yeah. I don't know exactly what are all the details of why this ended up being switched this way, but that's how it is. Okay. Okay, I think that is good. Yes. Okay, so coming back to your example. Let's do this in more details. Okay. So I think all of these will always have two. Let me call this tensor in bold. Just so that they don't have the same name. Okay. So in every case, we actually do have. So this link is actually okay. If we show the autograd meta. So this is the autograd meta. And this is also a C++ link. And this one points to the Pi node. Okay. So I think here is the first place where we have some potentially funky stuff. So the Pi node owns the function.
Hey Alvin,
I think
just a quick question. Can you stop sharing your screen so that we can see the whiteboard on
Yes.
Zoom?
Yeah. Is it better?
Yes.
Okay. Do you want me to zoom the camera a little bit?
Yeah, that would be good too.
Okay. So the Pi node owns the function, and I think in your case, we are so okay. So now as part of the Pi node setup, when you do save for backward, we basically take the tuple you gave us, and we stash that into what's the name? To save Python field.
Yes.
And then at the end of the forward pass, we will remove that and move that into a C++ saved tensors vector of tensor impulse.
And is the C++ saved tensor vector on the Python object or the Pinode C++ objects?
Exactly the question I wanted to answer. So here again, so we're in Python function on the Pinode. So this is Pinode and the THP function. So to save is here and save variables are here. So the C++ save variables are held on the THP function, not on the. So since this process has happened, actually we have now the function that holds through these saved variable field onto the tensor import of the thing we want to save.
Cool. And this is maybe pedantic, but in like as far as figuring out this ref cycle goes, does it matter that we had the Python to save and then the C++ to save in terms of like they represent the same? They don't change the graph of the cycle.
I don't think it does with respect to this high-level view. With respect to how to implement the traverse, I think it does.
I see.
Yes, that's why I want to go into so much detail of the cycle. So here, this tensor impl also have an autograd meta. And I guess the base is here. All right. Yes. Yeah. So then the important thing to keep in mind here is that this has a tensor because that's your output, I think.
That's right. That's the output. Okay. Also, to be pedantic, I guess the second autograd meta that you mentioned is an autograd view meta. So it's like a different object from the first autograd meta, because this is the thing where the thing we save is a view of the output of our autograd function.
So we have two tensors. This is good. This is good. I think these grad FN. Yeah, this is a Pi node. We good. And I guess in the end state of this whole shenanigans, we don't actually have a reference to that tensor from Python anymore. So we can assume that we ended up in the state where the whole thing is probably orphaned.
So actually, when we were looking at it last week, didn't we see that when we use that tool to see like what are the number of Python tensors that are currently outstanding, we saw it increment every iteration. So doesn't that mean that there is a Python reference floating around somewhere?
Oh, there is. this is the tensor, but that's what I mean. The tensor impl now owns,
Oh, and that's the only outstanding
Yes.
Python reference. Okay,
and that's why you leak 2 tensors and a custom function, I guess. That's
great.
pretty much your answer here.
Wait, hold up. So you're saying that we're assuming there's no other Python stuff because then we wouldn't have this like orphaned ref cycle business in the first place.
I'm saying that because, well, I think we're in this state, and the reason is because here we're not looking at like while the repro is running. We're running the repro is done, everything gets deleted. You're outside of the user function, so everything went out of scope. So you would expect that everything would be dead.
Oh, and this just didn't get cleaned up.
Yes.
On the Python side. Okay, got it.
I think the one thing though that is important is well, we will have to assume that the user didn't do any super funky stuff like make this tensor reference this one or something like that. But let's work under that assumption. I think it's fair to do. Like I don't think there is any Python links here because this was properly deleted. So the function shouldn't hold on to anything we care. This tensor doesn't have a grad fn in your case, right?
That tensor is only saved for backwards.
Yes.
Yeah, it's not returned as an output.
Wait, question. So the first tensor on the top is a input or output. So the output contains the graph-in to the Pi node, right?
Yes.
So that's an output.
Yeah.
And then the other tensor is a input then, right? So you're saving an input as a variable, or you're saving an intermediate.
It's a non-differentiable output in this case.
Okay, so it's not like detached or anything. What is
It's a no. Well, the temporary fix is to detach it to break that thing, but no, it's not detached. It's just any non-differentiable output of
saved as is.
that was saved for backward. Yeah.
Mm-hmm.
This is my check for understanding, but it's not in this specific case. It's not actually an output of the autograd forward, right? It's only like saved for backwards.
Oh yeah.
But it isn't like directly an output. Instead, its base is an output.
Sorry, what?
Like the bottom tensor is only saved for backwards, and it's not an output of the autograd function.
Okay.
But its base, which is the top tensor, is an output of the autograd function.
Yes,
So is it most likely that it's like an intermediate calculation or something?
it is.
Okay.
Yeah. And I guess one quick piece of context is basically like AOT autograd will construct this like giant massive autograd function object that like represents colon compiled forward graph and compiled backwards graph. And it can do all sorts of crazy stuff in terms of like what it saves for backwards and what it returns as an output. And so it's like technically possible to return an autograd function that exhibits like this behavior.
Yeah. Also, the other thing is if this was actually a differentiable output, we would probably detect it when saving it, and we would do something different here. And we would unpack it and do a whole bunch of other stuff with it because otherwise, if this was an output and it would save it this way, there would be a direct link here. That would be clearly a ref cycle. So we do a whole bunch of logic when we save it to not create that. But in this case, because it's not a differentiable output, we don't have to break that cycle, and so we save it as is. Okay. So then the question is, okay. So now, any question at this point about the whole cycle? No.
I guess the one thing apparent to me from this is that it's not like, it's interesting that it's a huge reference cycle with a bunch of things, and only one of them is a Python object, and everything else is a C++ objects.
Yeah. Yes. But yeah, but the GC does trigger on like all 3 of these.
Yes, yeah. But then triggering on the left 2 tensors won't actually like touch the cycle at all.
Yes. Yeah, that's a valuable question. Yeah, I think realistically, what we expect to happen is that traversing these will do nothing. I actually agree with you. Yeah, traversing these should do nothing, but traversing this one should see that I own this, which and also owns this. Like, yeah, I own this C++ object that owns both this tensor and this other tensor.
Yeah, is another.
And this object owns this.
So can I think of this in terms of what the Python GC should see? Is it should basically see one Python object that is effectively self-referencing. And so it's like a reference cycle of size 1 in terms of Python objects. And then we say self-referencing object is a cycle, free it, and then free all the related things. And all the related things is basically everything in the cycle, including the 2 extra Python tensors.
I think that makes sense to me, yes. Yeah, okay.
Could your cycle like jump to another cycle?
What do you mean by that?
I don't know. I'm just saying, like, could that output tensor at the top end up owning another loop?
Yeah. That should be fine. Yeah. It can, but the GC will handle that pretty smoothly. That shouldn't be an issue. Yeah. Okay. So I feel like I see 2 issues then, or like at least, yes, 2 issues is first, let's check what's the traverse, what this thing is doing.
Yeah.
Okay. So what's the Python?
Oh, so our like tentative theory from last week was, oh, we can update the tensors traverse. And that actually would not fix this at all, right? Because it's only the custom functions traverse.
I'm not sure actually.
Okay.
I think, yeah, that was going to be my second point, but so here we do visit all the Python objects properly. Like all of these Python objects that we have. But we do nothing with the C++ objects that we own. Namely this one. So yes, that sounds like a problem.
Makes sense.
But so just to give more context on where the problem is here is that even though we can say that actually this function owns a reference to that tensor ball, that owns a reference to that other Python object, so technically we should, we do want to traverse it. The problem is that we should only ever do that if there is no other C++ reference to that tensor ball. Because if we are not the sole owner of that tensor ball, destroying ourselves will not destroy the Python object.
Okay, that fits with my mental model of a bunch of the TP traverse code says if use count equals
Yes.
1 to this thing.
So yes, the thing we do is we have this thing where if we are the sole owner, and that links back as well to the multi-threaded case of like, if the use count is not 1, you cannot say anything because maybe another thread is using that same object. And so you don't know how the use count is or could be changing at the moment.
Can I ask not to totally tangent this, but is there, like, how does thread safety in that situation work? Is the idea that TP traverse is all happening under the GIL, and so you don't have to worry about any crazy race conditions with the use count changing?
No, you can't. But you are guaranteed that, well, in this case, that's why we check if it's borrowed before we check the use count. Because if I have an owning reference, so if I'm in this case, so if I have an owning reference to the tensor pool and the use count is 1, I am guaranteed that I own that reference. And I'm guaranteed that no one else has a reference.
Oh, okay.
And so you don't need to worry too much about thread safety because you know there is a single reference and you own 1.
I guess the situation I'm thinking about is what if the use count is 2, and then like right after that if statement runs, then the other thread runs, gets deleted, and then.
So the hope for this discussion is that you will end up in a steady state where, you know, every other weird stuff will have, because the GC can run regularly,
That makes
So
sense.
at some point, you should end up in this state with hopefully no other, like, all the other temporary C++ references and stuff will be gone. And you will get a clean enough graph. And by the way, like, the way we do distributed reverse on tensors for the grad_fn, that might happen if you have a couple tensors that reference two things at different levels in the graph. Basically, the bottom part has a use count of 1, and so will get deleted at that time. But the other ones above, because there is a reference from the other tensor through the graph. So every run of GC basically would delete 1, a little bit more of the graph every time.
Oh, that's interesting. Is that a real example of like you might need to run the gc.collect like multiple times for something useful to happen?
I don't think I've ever seen that happen actually in practice, but theoretically, I think yes. I'm sure you might be able to craft an example where that would happen. Yes. Yeah, I'm sure Greg will twitch at the memories of the PyTorch days, where you always had to GC twice to do anything, which was weird. Anyway, okay, so yeah, definitely first thing is that okay, and then I guess let me go to the second point, which is I think these things are like weirdly a single object. And so we should treat them as such. So like, the TP traverse on the tensor object, should make sense even if the arrow is this way. So it's not like because this owns the tensor object that I should not traverse. But
so that makes sense. And I guess the other thing you're saying here is that TP traverse will never be called directly on that red tensor impl. It'll be called on some other Python objects. And that Python object's TP traverse needs to be implemented to manually like walk through the C++ pointers.
Well, yeah, TensorFlow doesn't have a TP traverse. The Python object because it does. But assuming we don't have any C++ reference anymore, in this state, how do I know, to tell Python to traverse these things? Because this technically owns a reference to that tensor. But we also want to say that this owns a reference to that other tensor. So, I think it does make sense to consider these things as like a single block where, I'm traversing the tensor itself, the Python object tensor that can say it owns this thing.
I see. Okay.
Because technically, if you were to actually clear this function, you would destroy this object that would in turn destroy this object.
Okay, and double checking that last thing, it's not that you're saying destroying that bottom green tensor would destroy the top green tensor, or in my mental model, it would just be they get independently destroyed. It's like they're all things that are owned by the ref cycle. So
yeah, I think that's where we kind of bending the rule here. Where the traverse should be saying that this object owns this one, but because the way we do the weird ownership, you could glove these two together and pretend they are a single Py object.
Okay, double making sure I understood that last thing. Are you sort of saying are we morally telling the Python GC that there's a ref cycle between those three Python objects? Or are we morally telling it that there's just ref cycle of like a one thing, and then the other two are kind of byproducts?
I think we could do it both ways. Okay. And I think my second point is, I think it's going to be simpler to block that as like, this is only a Python object. And so this owns this tensor, that owns this tensor, that owns this thing.
Yeah.
Because then we have to traverse to implement properly and the whole thing will work. And we don't need to, from here, manually traverse all these C++ objects to go back here.
Okay, I'm curious how we avoid that manual traversing. But
well, you just do one step, right? The function just need to traverse the tensor in the state variables, right? So that's one fix we could do. Just say, if I'm the sole owner of the tensor info inside the save variable std vector, I should traverse it when I traverse this.
One question I have, I missed the first half, so this may have been answered, but does the function go out of scope are we assuming that goes out of scope first? That like what kicks off? I'm just trying if you're traversing, and again, I missed the first half, so that's maybe a dumb question. But like starting from the function in that traverse, I know we don't currently traverse over saved variables, but like, do you visit the green tensor first, and then you have to know to look at the tensor impl that only has use count of 1, or do you go to the tensor impl first, and then since that references the Python tensor, it's gonna GC that?
So the other the objects get traversed by the GC is
Yes.
arbitrary.
Okay.
But it will only traverse the Python objects. So only the Python objects will actually be traversed.
So go right green function to bottom green tensor.
Well, that's a question. What
Yeah.
is traverse?
Yeah,
that's yeah.
Yeah.
Yeah. I think my point was what is a good constraint so that when these should traverse the tensor object itself.
One thing that feels like a pitfall to me, but maybe is not based on what you're saying, is if we treat those two, the red and the green tensor, as a single entity for the purposes of this ref cycle, that means, so we didn't draw it here, but there's technically like a weak ref arrow pointing in the opposite direction from the green tensor back to the red tensor impl. Is that right?
Yes.
And is the idea that like when we call when we effectively recursively or not when we effectively visit that green tensor on the bottom, we need to traverse that weak pointer to its red tensor impl to sort of keep going.
So
yeah, sorry.
No.
The one like thing that I wonder is a pitfall is like, do we always want to do that, or is it sort of in this unique case that we want to sort of traverse that weak pointer?
So I think in this case, you do want to do the func traverse these save variables. I think it's going to be if and only if this is in this direction, which is when the tensor impl owns the tensor. Because if the tensor impl owns the tensor, that is guaranteed that there is no Python reference.
That makes sense. But then what'll happen later is then we end up calling traverse on that tensor, right?
And sorry, tensor impl use counts. So I'm the sole owner of the tensor impl, and there is no reference from Python to the tensor object. So basically, you are guaranteed there is no arrow coming in or coming in from here.
Yeah.
And so in that world, I think we should traverse these tensor objects.
Yes. And then when we do that, the next thing that'll happen is that TB traverse will be called on the bottom tensor.
On that tensor object, yes. So I think that's one change we want. And then the second change we want is on the tensor object, we need to make sure that from this we go here, and from this we go here.
Yeah, the sort of case that I'm having a hard time picturing in my head is when we do that second call, like what we're going to see is we have a tensor that has a weak ref to its tensor impl.
Yes.
And do we need some custom logic to say only in some circumstances do we cross that weak reference, or is it okay to unconditionally cross that weak reference? Like, do we somehow need to detect that we're in this situation when we're doing that, or is it okay to just say it's always fine to traverse like in that direction?
That's a good question. So let's try and answer that. Maybe that didn't work. Okay. So the case where this would happen is if you have some C++ object that owns the tensor impl, and you are currently traversing this. Yes, I agree with you that you cannot assume that you own this at this point. Yeah.
But you can't assume that you own what?
Sorry, you can't assume that you own everything that is here.
Yeah, that's
Because you don't, technically.
because all you see is the weak ref, right? So
Because all you see here is the weak ref, yes.
is it okay to just look at the use count though of the tensor import?
But even if the use count is 1, you don't know where that, like, in this case, we care, like, we know it's okay because we are the one from here that says, I own this and I want to traverse it. But from this, like, if you didn't know where this was coming from,
yeah,
this could be any arbitrary C++ object that just owns that tensor for a very valid reason. And you do not want to destroy that. Maybe you have the loss that is a grad fn, that is a bunch of grad fns that point to that tensor symbol. That is a very valid thing, and the loss might be still alive, so that whole chain needs to be kept alive.
Okay. I'm wondering what you think. My thought is like it's still okay to traverse because all we're doing at this point is traversing the pointers. So that still seems okay, but that might be wrong.
Well, the rule for traverse is that if that object were to die, this is all the things that would die with it.
Oh, so like
Right.
it gets killed otherwise. Oh, sorry, Idris.
No, it's like I'm just like, how would you in this case though, isn't there only one way we can get to the green tensor? And like by getting to the bottom Python tensor, you're like assured to be in that case where you can cross back.
Well, I feel like we might need to have a special function on the tensor object or on the tensor pair here, so that the function can say, hey, I guarantee you that you're gonna die. Do a traverse as if you were about to die. Because in it, it's like if the GC equals TP traverse on that tensor, I do not want to mark this as traversed. Because that's not true, right? This tensor object does not own this one. But if the GC equals traverse on this, I want a way to say I own this one and I own this one. And so I can say I own this one, that's relatively easy. But this one in vacuum doesn't know if it should own this one or not. So
Guess we need another bit on tensor import.
no, I literally mean we just need to expose that as a function on the THP variable, or like on the tensor Python object. Just like we have TP traverse, we can have like you want to call TP traverse with a special flag that says, hey, like you don't need to do action at a distance on this thing.
Yeah.
You can literally call it from here. The whole, like, you could also just say, I ignore this thing, I traverse this, and then I keep going through the chain. It's just simpler to, have the logic within the tensor itself.
That makes sense. I mean, we're like eventually we end up calling the actual Python TP traverse, and like it needs to find that state from somewhere outside of the current function context.
Well, I think my point is the regular tensor TP traverse should not. But the tensor object should have an, extra traverse method that you can call, and the extra traverse will do the traverse from, the point of view of this one.
So you're saying we won't even use the existing TP traverse at all?
No.
Part of tracing.
Yes.
Okay,
Yes.
so the thing that was in my head that is probably wrong then is I assume that TP traverse is this mystery box that like does other things that are totally opaque to us. But I guess no, it's just like an ordinary function.
Oh, yeah.
You can swap that for something else.
Yeah. Yeah, it's just an ordinary function. You just need to call some specific stuff, some specific function within there, but yes. So the regular TP traverse will still do the thing you expect it to do. And in some cases, it will actually call this extended traverse, or like this owning traverse function, I guess we could call it. But you also want the option for this to directly call the owning traverse because you know better, kind of,
Right.
And this will be useful for the second tensor one as well, right?
So, well, that doesn't get us out of the weeds yet. So that would solve this direction. Okay, so then what should we have? Look at this. I think this direction should work, and I think that's what we're looking at. But basically, if the tensor, like again, if this blob, like assuming you're in a case where you own the tensor pool, these blobs should call into. We are going to check. We should check the grad basically, and if it is a pi node, we do traverse it, and that we do. I'm pretty sure
that happens today.
Yes,
It's not just from looking at this picture, it's not clear to me why that's the case because it seems to me like we have the same like weak graph problem of like you're calling traverse on the green top tensor, and how does it knows at this point that it doesn't own the tensor at full. So why would it know to traverse?
Well, can't you just call special traverse from within special traverse?
Yeah. You would need to call that.
Okay, so it can't use the existing logic then, I guess.
But yeah, during the traverse, we have this weird thing where we say, hey, if you actually have a pi node, we care about you and we're going to visit that pi node. So if you have a pi node, we will visit the Python object associated with that pi node. So from here to here, we are doing the right thing already.
Well, aren't we only doing the right thing in the case where the green owns the red tensor?
Yes, yeah. Okay. Yeah, but again, modulo that refactor where we say we have a way to, visit this in a way that I pretend I owned it, like that the tensor owns itself. Got it. So that's this one. But if you look here, so again, in under the assumption that we are owning, so the Python side is owning the C++ side, we do this thing, and if we have a use count of 1, so no one else, keeps it alive in C++. If there is another grad meta, so the grad fn thing, we do traverse, but as we were mentioning, the autograd view meta, we do not traverse anything there, but the autograd view meta actually can contain the tensor. And I mean, this link is missing for sure.
I'm curious if you think this will fix any like completely unrelated ref cycles. Because you're saying there's this second bug that would never traverse the view meta. And so
I think in general, the idea is that the whole autograd stuff is designed in such a way that all the links, or like all the reference goes in a single direction. From the lost object, it goes kind of up the grad fn, the parents, like, because all of these objects are created in like a temporal order. As you run the forward function, we create more and more objects within autograd. And so usually all the links go up. And so, a tensor and its base, the base has to be older than the tensor. And so the link goes up. And the same way the grad fn links goes up. Like every link usually goes to the older objects. And so that's why we usually don't have reference cycle. Like you have to try hard to get a reference cycle in these things. Or like do these kind of weird thing where at a single place, so on the exit of the custom function, when we set up the graph, we end up in one of these cycles where an older object basically gets referenced by a newer custom function that we just created. And that's a weird direction to have. Yeah. Because we have an old thing that keeps alive a new thing.
Okay. And one last question that's perf related, which is given what you just said about like, okay, we're not currently traversing the autograd view meta at all today. This is a case where we only actually need to traverse it in this weird case where the C++ owns the Python. I'm curious if you think, do you think there's perf implications to always traversing the autograd view meta and therefore making our like TP traverse slower, such that like we should only do it in this specific case, or do you think we should just always traverse it?
No, I think we should always traverse. It's a very cheap check.
Well, the like vague hand wavy reason for that in my head was you were saying at the beginning of like we want to make sure we don't accidentally traverse the whole autograph graph.
Yes, but this one is a one kind of like constant distance kind of deal. So just like, when you visit the grad FN, we could keep going through more grad FN if there were more, but we don't do that because it's kind of unbounded. But this one is bounded, it's like it's one distance and this is one distance as well.
Oh, okay. So the way that would be a problem would only be if we go from grad FN to grad FN, like we're
Yes.
through more and more grad FNs.
Yes.
But like tensor grad FN is always fine.
Yeah.
Okay.
Okay, I think we have one more minute if anyone has any extra question.
Did you have an unbounded autograd view meta linkage, like a view of a view of a view of a view?
But so the difference here is that technically each tensor will only traverse until the next tensor, and then we'll traverse that tensor. It's very different from going through arbitrary number of C++ objects until you eventually reach a Python one. And here the ownership is very strict, right? The autograph view meta has a single owner every time. And the base here, we will need to do a use count check again. But it's a lot simpler and direct. Like if you go through the grad FN in C++ world, it can be quite. You will need to check every use count of everything all the time. Okay. I think we're running out of time, so we're going to stop here. I guess, Brian, we're going to follow up on this.
Sounds good. Yeah, that was super helpful.
Yeah. And do ping me if you have any questions on this. Anyone? Thank you.